We're now going to start our second unit on stars, and as such, we're going to start with the star that's very close to us, which is the sun. Now, why start with the sun? It's because it's right there and it's what we know the most about. And as we understand more about the sun, this is going to lead us to start understanding more about other stars in general. So we'll start with the sun. Again, the sun is the star that is very closest to Earth. It is actually the sunlight that warms the Earth and gives it the pleasant temperatures that we all enjoy, or mostly enjoy. Based off of what we've talked about previously, the sun has a surface temperature of around 5800 Kelvin, which we can tell based off of the color of the sun, but also based off of its spectrum. The sun is the only object in our entire solar system that actually produces its own visible light. Everything else we see is because of reflected sunlight. Now, because the sun is the only thing that gives off its own heat and light, then it's reasonable to start wondering how. Well, anciently, as people were considering this, the only other thing that they knew of that gave off heat and light was fire. So it was figured that maybe the sun was a giant fire burning off in space, a giant lump of wood or coal or something like that. Well, based on the amount of energy that wood and coal store and how fast the sun is producing energy, we can actually figure out how long such a burning lump of wood or coal is actually going to last. Well, when we run through all of the numbers, as something as large as the sun burning as giving off as much energy as we see the sun giving off, this would last for about 10,000 years. Well, that's not nearly long enough. Definitely something else going on. And so later, it was realized that as things compress, they naturally heat up. So if the sun is still shrinking, then it could get hot enough to glow the way that it does and give off the heat that we experience. And so people figured out how long would the sun last if it was still shrinking to glow and so on. Well, this number is about 25 million years. And this is a much better number. 25 million is really good. But again, it's still not good enough. If you remember back, the extinction of the dinosaurs was about 65 million years ago, meaning not good enough. Definitely have to have something else going on. Well, our first clue for the source of the sun's energy comes from the equation E equals mc squared. So if you remember back, E is energy, m is mass, and c is the speed of light. So this tells us that we can convert mass into energy, and then later on we'll talk about how energy can be turned into mass. Now, part of what's important is this c squared here. C is the speed of light, and the speed of light is 3 times 10 to the 8th meters per second. In other words, that is a very large number. So c squared means that it is you multiply the speed of light by itself. So if you have a large number and you multiply it by a large number, you get a really big number. This tells us that in just a little bit of mass, we have lots and lots of energy. So if we can convert a little bit of mass into energy, it's going to give a lot of energy off. Well, it has been shown that the temperatures and pressures at the center of the sun are sufficient to lead to nuclear fusion. Nuclear fusion is the process where we combine the nucleus of atoms together, and because we now have a different number of protons, we're actually converting one kind of element into another type of element. For the sun, it is converting hydrogen into helium. And as this happens, a little bit of matter is going to be turned into a whole lot of energy. Now, the process of fusion occurring in the sun is hydrogen fusion because that's what we're fusing together. This is also sometimes referred to as hydrogen burning. Now, I want to make a distinction though. This is not a chemical process. This is not like a fire that you experience here on the Earth. This is a fusion, a nuclear process where we're combining the nucleus of atoms together. So although we refer to it as hydrogen burning, it is not chemical, it is not normal fire. So we call it hydrogen burning because hydrogen is the fuel that we are using. Now, the type of hydrogen fusion in the sun is the proton-proton chain. We're going to see another type of hydrogen fusion later, but for the sun, it's the proton-proton chain, and this is the way it works. We start out with 2 hydrogen nuclei. The nucleus of normal, boring, everyday hydrogen is just a proton. So we start out with 2 protons. These 2 protons then fuse together. However, in this process of fusion, one of them spontaneously changes. It turns from being a proton into being a neutron. I realize that sounds weird, but it's allowed. Particle physics is kind of strange. But in this process, it gives off a tiny particle known as a positron. A positron is a type of antimatter. The idea of antimatter is that for every particle of matter, there is an antimatter equivalent. You can kind of think of it as mirror matter, a mirror of normal matter, but even that is not exactly right. Anyway, but for every matter particle, there's an antimatter equivalent. The antimatter equivalent has the same amount of mass as normal matter, but it has opposite charge and opposite quantum mechanical things that we're not getting into. Okay, so as an example, we have the matter particle, the electron. The electron has a negative charge, so its antimatter equivalent has the same amount of mass, but will be positively charged. That is what a positron is. Okay, so it's a positively charged antiparticle that is the match to the electron. Okay, well, when matter and antimatter come together, they annihilate. What this means is they go from being mass into being pure energy. So in this process, the positron and an electron combine, which creates gamma rays. And if you remember, gamma rays are the highest energy form of light. So right there, we just produced a whole bunch of energy. Also in this process, we will release neutrinos. Okay, a neutrino is a tiny ghostly particle. It is even smaller, significantly smaller than an electron, and it has no charge. What this means is that it does not interact in any strong way with normal matter. It's actually able to stream directly out of the sun. This is going to become important later on, so just note that at this point we're producing neutrinos. All right, all of that is still step number 1. So we've combined 2 hydrogen nuclei to form hydrogen 2, also sometimes known as deuterium. We then take the hydrogen 2, the deuterium, and onto it we then fuse another hydrogen 1, or normal hydrogen nucleus. This then produces helium 3. It's helium because it has 2 protons, and it's number 3 because it has 2 protons and 1 neutron, 3 total particles in the nucleus. In this process of fusion, it then gives off another gamma ray, giving off a little bit more energy. In step 3, we then take 2 helium-3 nuclei, fuse these together into helium-4, which is normal, boring, everyday helium. This then also releases 2 hydrogen nuclei. So you don't actually have to memorize everything about every single step in this. What I do need you to remember is that in this process, we convert 4 hydrogen nuclei into 1 helium nucleus and a lot of energy. Okay, this is the big takeaway for the proton-proton chain. Now, through this process of nuclear fusion, based on how much energy is released and how much fuel the sun has, the sun will burn as it does for a total lifespan of 10 billion years. Based on other evidence that we'll talk about later, we believe that the sun is about 5 billion years old, which means that it's got about another 5 billion years to go. In other words, what this means is when you wake up in the middle of the night in existential dread, worrying about all of the different ways the universe can kill you, you do not have to add the sun suddenly disappearing to that list. It's got a good long time left.